Hello, and thank you for joining today. My name is Todd DeCapua, and this is a Vivid SIG talk. It's one that's going to be a lot of fun. It's around quality and testing. So you're going to hear from three different futurists today on two major topics. And the title that we've come up with for this is The Future of APM, Telemetry and Blockchain. Today is the 14th of August, 2018. You're either joining us live or you're listening to it on the replay. As we go ahead and get started, I'm going to make some very brief opening comments and then go into introducing today's speakers, get some housekeeping out of the way, and we will then get started. This whole program will be an hour. The objective of Vivid SIG Talk is to provide you with three different presenters in 15 to 20-minute segments. So there's a lot of content you're going to get very, very quickly from each of the three presenters. These will be available, again, as a full replay or individual Vivid SIG Talk replays. So again, if you want to learn a little bit more, if you want to ask any questions, you can use this hashtag Vivid SIG Talk on Twitter. This is being monitored for Q&A, as well as anything else related to learning more about Vivid or learning more about the Vivid SIG talks. As you're looking across what was the end of 2017 and also all of 2018, you might be interested in participating either as a listener or also as a Vivid SIG Talk speaker. There are still a few more sessions remaining this year. As you can see, if you would like to contribute or participate as a speaker, there is a survey that you can either get the link from the PDF that's available for download after this event. It should be posted within 24 to 48 hours on our website, and you can hit that hot link, or you'll see the survey also at the end of this session. But I'm always looking for industry professionals just to share their ideas on different practices that you may have picked up along the way, and you can see as they would relate to things like proven practices, tools, or other testing tools that might be out there that you are using today. Again, a very brief introduction. My name is Todd DeCapua. I am an executive director here within global technology for JP Morgan Chase and Company. I'm also a volunteer with Vivid Worldwide and sit on that board of directors. I am joined today by two other individuals to round out the total of the three sessions. You can see the second speaker is going to be Matthew David. He is a senior manager overseeing and responsible for mobility, IoT, and user experience with Kimberly-Clark. And then third speaker today is going to be Zach Cole. He is the CTO of a organization called White Block. So again, we will learn more of each of these speakers. They will be doing a brief introduction of themselves at the beginning of their talk as well. This is a live session. It is being recorded. As I mentioned on the first slide, they are going to be available to all Vivid members. All of you should be Vivid members. If you want to tell your friends about Vivid, it's free to join, free to access all of this content, and you can also share that with other folks as well. Please type any questions that you have in the questions pane. So again, as you see that over to the right-hand side, we have allocated time at the end of the talk for answers to any questions that you may have. Some of the logistics around that webinar control panel and where specifically you are to type in those questions. You can see here visually an example of what your window should look like. And for the Q&A piece where it says type your questions here, that's where you type it in, and then just click send, and we'll be able to go ahead and see that on our views as well. Again, another option for you, tweeting your questions to Vivid SIG Talk, just leveraging the hashtag. So without further ado, let's go ahead and jump in to our first Vivid SIG Talk of the three for today. My name is Todd DeCapua, and I'm going to be sharing a little bit with you on a topic that is very passionate and very close to my heart. It's around telemetry. And as I think about telemetry, this is really the essential ingredient to success with Agile, DevOps, and SRE. So it seems like no matter where I go, no matter who I speak to, you're somewhere along the lines of one of these journeys, or more than likely one or two, or perhaps all three. So as I've used a variety of ways to think about and to create and to visualize telemetry, I always find this a fun conversation to have with many different layers of folks, but it's one that I want to be able to provide to you as practitioners to be able to pick up maybe a few of these points, maybe just lift the content that I've provided to you and be able to have these conversations within your organizations. And again, this is all about telemetry. You can see how, as we get into the conversation, this is the essential ingredient to success with Agile, DevOps, and SRE. So as we first jump into this, I often like to start with the why. Why is it that people are going to care about telemetry? You can see here a number of different points, number of statistics, but as you ask this question, why, typically I'll get any one or perhaps all four of the boxes that you see dead in the middle of your screen. So we want to be able to increase our speed, the speed of, hey, I've got a great idea, to being able to put it into your customers' hands. Second, reducing mean time to resolution. So again, as you would have a production incident, how do you get back into normal operations, and how long does that take at a mean or potentially an average? Third, increased collaboration. Again, collaboration across the teams, collaboration with your customers, collaboration with your partners. And number four, the highest value customer delivery. So this is really, we all know that we've got a limited amount of resources, whether it's people, whether it's money, whether it's time. How is it that we can ensure that what we are delivering is ultimately the highest value to our customers? So these are the four reasons why. Supporting each of these and providing a little bit more of an insight are the four metrics or statistics that you see surrounding them. I've also created or included a hyperlink to more details of where these quotes came from. The other thing that I find interesting is in all of the looking around that I found through various analysts, other outlets online, and just leveraging many search engines, I've not been able to find a lot of the why specific to telemetry. And what you will see is this is the why as it would relate to things like DevOps. So there's a lot published there. I think soon you will start to see more published around the why of telemetry. And again, how telemetry is this critical capability that is essential to success with Agile, DevOps, or SRE. But again, as you look across here, you can see the increasing speed piece. Within this link, there's a Capital One case study where they were able to see a 20 times increase in the number of releases over the same period of time. As far as mean time to resolution from the Puppet Labs research that was published from 2016, they found a 24 times faster recovery from failures. As we move to increased collaboration, this infographic journal found that, and this was actually number one in this survey, why do organizations need DevOps? 47% of them said better collaboration between development and operations team. And then as we look to the bottom right, again, a Puppet report, this one I believe was from 2017, around this highest value customer delivery. By using DevOps, there was 21% less time spent on unplanned work and rework, which resulted in teams and individuals being able to spend 44% more time on new work. So again, this is a bit of the why around telemetry. And again, how is it that you're able to visualize those results that you're delivering? How is it that you're measuring what you're doing? How is it that you're measuring your end customers as well as your applications and your infrastructure? All of this probably makes sense as to the why. The next part that I have to help people to understand is, well, what is it? And it's kind of humorous, but I like to use the analogy of it is rocket science. So, as you think about a telemetry system, and we think about rockets, and space and everything else that, you know, a lot of us enjoy kind of joking that it's not rocket science. Well, let's use that analogy. So you've got an airborne system in a rocket. There's a variety of sensors on this rocket. You know, we're going to think about things like an accelerometer, temperature, pressures, you know, heat, you know, that would be inside as well as outside. There's all of these other sensors that are on any rocket system. How is it that that gets communicated? How is it that that gets recorded? Again, you can see coming off of this airborne system, things like radio, cable, you know, there's wireless, but this is distance, you know, so we're talking about up to billions of kilometers away. We need to be sending these types of messages. We need to be recording them, all of that being sent over some sort of a time series to a ground system, this then being visualized within some sort of a computer display. So I love to use this analogy as we just get done talking about, you know, why is telemetry important, and then we get into what is it, to provide a fairly layman introduction into telemetry. As we move forward, you know, how does this fit together in this broader conversation? Again, I like to use these 4 elements to help articulate this. So there's things like collectors, and I'll get into each one of these components here next. But you've got collectors that are able to collect different pieces of data, report on metrics. That data, how does it come in? How does it get normalized? We'll talk a little bit more about that. Visualization, how is it that you can help to provide a quick and easy way for people to see what's going on and make informed decisions? And then ultimately, telemetry is what ties all of these components together. So as we jump into this collectors component of telemetry, you can see there's a number of elements on here that you could speak to. Again, I want to encourage you to take and lift and use and steal as much of this content as you feel relevant to help you in having this conversation with your organizations and your customers. But around collectors, there's things like performance, there's capacity, there's monitoring, there's production incidents, there's security. I'm sure you can think of many other elements of content and data that you would want to be able to consume or collect. Very specifically around performance, I think it's easy to think about things like performance testing results. This could be, you know, how is it that my application performed while we run a load scenario in a pre-production environment? How is that relevant for, you know, performance of an existing system in production and how it's running? What if I could then compare the two of those, know that there's a linear difference between pre-prod and prod, but now I can apply some predictive analytics to that telemetry that I'm able to collect. So that is one very quick, simple, and easy example of a collector, understanding what performance is and some of the specifics about how you can collect that information. That data, so again, maybe you're running a tool like LoadRunner, Performance Center, BlazeMeter, JMeter, Gatling, any of the above from a performance perspective. Where is that data stored? You know, how is it that it's structured? So now all of these questions around telemetry data come into play. You know, what is that data architecture that you have? How have you normalized all the different data components that are coming in? Again, do you have some sort of a data dictionary to define, you know, TPS equals transactions per second? And you know that any data that's now stored within your, you know, data lake, data ocean, if it says TPS on it, you know exactly what that means, and it could be applied and used across any of these different sets of data. We then get into things like data streaming. So one of the more popular ways to do this today is through things like Kafka. Also machine learning, artificial intelligence, and predictive analytics come into play around data as well. Being able to apply those elements across larger time series data sets to then be able to start factoring some fairly interesting insights that you may otherwise not have. But again, this very quickly covering off on data as it would relate to telemetry. So this is all well and good, but I want to be able to visualize, you know, all of this information, and specifically to things like alerting, event management, dashboarding. There's many other consumers of this data that you would imagine. So where we talked about data streaming, again, is there a topic that I could subscribe to be able to consume that data and then be able to visualize it in whatever tool I may want to use and be able to come up with my own results. But knowing that that system of record or that core data is the same and intact. And again, we can go back and we can trust that data. But as you think about things like alerting and event management, this is really on the production management side, or operations, command center, mission control, whatever you may call it. I've also seen where development teams, QA teams, all of your lower environments, they also want to have some of the same alerting and event management within those environments so that they can reduce the amount of downtime in their pre-production environments, and also provide an opportunity to test that alerting and event management that they ultimately will have in production. Dashboarding, again, this can take many different shapes and sizes. Today, many tools offer dashboarding natively in their UIs, but there's also many different open source visualization tools that are out there that could leverage, again, all of this data, enable you very quickly and easily to visualize your results. As we kind of roll through the last bit here around telemetry, one of the fun pieces coming out of telemetry are things like observations. These typically come with being able to correlate the variety of different data sets and coming up with some aggregated metrics that have meaning as you then think about them over time and compared to each other. We mentioned the variety of topics, alerts, and how is it that you're doing event management? Again, do you want breadcrumbs that go back to that native collector tool, or we use the example of a performance tool to be able to specifically dig in and see what were the results? And if I'm in the middle of an event management scenario, can I look at those details by simply clicking a button to see if there were anything that was unique that was happening that may have caused that existing incident? The visual example here in this image is that of an F1 racetrack, and you can see there's a number of different data elements on this single screen. But I've had the opportunity to work on a very similar scenario within NASCAR, and what I will tell you is all of these various ways that are capturing data and all of the varied sensors, you can only imagine what's being consumed. This then providing them a way to easily correlate and have observations of near real time that's going on the racetrack. And the reason I like that example is I think this is very similar to how many of us are required to run, whether it be in your lower environments or in your production environments. So again, this is a very real example of how telemetry provides that full picture. As we talk about success with Agile, DevOps, and SRE, there are a few references that I've leveraged throughout my career. I always love to share a few of those. These should be familiar books to you, all of them being available online at a very low cost. And I know of at least one which is still free, I believe, with the SRE book itself. But again, if you have not had an opportunity to check out Ken Schwaber's Agile book, often referred to as the Colors Agile Software Development with Scrum book, highly recommend picking that one up to learn a little bit more on some of the basics of Agile Scrum and how telemetry will play a factor there. DevOps, Gene Kim has put together this book with the Phoenix Project, and Betsy being one of the main editors on the O'Reilly Site Reliability Engineering book. So with that said, I am going to go ahead and turn over the mic. I am wrapping up the session on the essential ingredient to success with Agile, DevOps, and SRE. And Matthew David, you are up next.
Awesome. Thank you very much, Todd. Great presentation. One of the things I want to kind of pull out from Todd's presentation there is the ability to be able to use the tools that he was talking about to free up time with your DevOps teams to be able to implement greater numbers of features, including new and emerging features. The subject I'm going to be covering here is blockchain, but one of the things that is really becoming epidemic right now in a very good way is just the sheer volume of new technologies that have ways in which they can help transform how we deliver successful solutions that delight our customers. So I'm going to focus on blockchain, but there are other tools you can use for that extra 44% of free time that comes up. So what is blockchain? There's a lot of news that's out there right now. Essentially, there's a lot of fear and uncertainty and doubt in that news, and that's driven by what happened in 2017 with the rise of the cryptocurrency bubble, really led by Bitcoin, and that bubble spectacularly exploded at the end of 2017, beginning of 2018. And has had a hard time recovering in the last recent months. The thing you have to bear in mind, though, is that we are going through really an evolution, and a very rapid evolution, of ways in which we can deliver solutions that are part of what we're calling Web 3.0 technologies. And blockchain is a foundation to that. If we look at what happened with Bitcoin, the reason why Bitcoin grew and became so successful over a number of years is largely because of the way in which the transactions and the data was being managed. So if we look at what a blockchain is, and that's the technology powering Bitcoin and other protocols such as Ethereum, a blockchain is essentially a peer-to-peer network where called nodes, where you have a distributed ledger shared across that network. And you can think of the ledger as an Excel spreadsheet or a database that every time a transaction or a entry is made into that spreadsheet, there has to be consensus agreed upon the transaction for the whole network. And what that essentially gives you is this opportunity to be able to share data more easily and freely with your groups of followers or people who you're working with, but also allows you to actually grow the type of data that would be essential for you to grow your business. So a good use case would be in supply chain, being able to have all the people within your supply chain having access to the same data. The way that blockchain itself actually works is that, if we go on to the next slide. I'm just having a problem here, but I'll just wait for the next slide to come up. So the way the blockchain works is that you start off with a piece of data, and that is a block. Then as you make a change to that data, we use cryptographic caching to secure the actual entry. So the actual data itself is really, really secure. What's interesting is that every time you make a change to the data, instead of rewriting the data, you actually append to that entry. And as you keep appending, you start to create additional blocks or chains of data around that entry, and hence the name blockchain. And the benefit that you have from this is that the data itself, you can actually go back and you can have auditing as a byproduct for that data. And I'm just going to have to restart PowerPoint. Give me a moment here. So auditing becomes a byproduct of that data, and it allows you to then also share how that data and who you want to have access to that data through the encryption. I'm just going to go ahead and reshare my screen here.
Matthew, I just sent it back to you. See if that works, and if not, we'll have Todd pull it up. Perfect.
Okay, looks like we're going good here.
Yep, and then just go slideshow mode. That'd be great.
Alrighty. Okay. So I'm seeing that it's paused. Can we?
Okay. Do you want? I'll give it back to Todd, and he can try them for you. Because it seems to be frozen. Coming at you, Todd. All right, there we go. Sorry about that.
All right, no problem. All right, so let's look at some of the use cases that we have for blockchain, and I'm just going to go through just a couple of these. Supply chain is one that I spend a lot of time talking to manufacturing companies about. Right now, there's challenges with visibility of products as they're moving through the supply chain. So consider something like the romaine lettuce issue that we've had, where people have been getting E. coli from the lettuce. The problem we have today is we don't really know specifically where the lettuce came from. We kind of have a rough geographic idea where it came from, but there's been a lot of money spent on actually understanding where the lettuce came from, and just the whole auditing that went around that, in conjunction all the time that was spent on the negative press. If we go on to the next slide, we can see how blockchain could potentially address that issue with supply chain. Think of blockchain as becoming your record of entry, your true north. But blockchain becomes really powerful when you start augmenting it with technologies such as IoT and machine learning, and other what they call oracles or APIs that you can connect into your blockchain environment. So blockchain becomes your system of record. So you take your romaine lettuce, and when you actually harvest the lettuce, you could actually then make an entry into the blockchain and say, this is where the lettuce was harvested, and you can then potentially then pull in additional data from APIs on weather conditions. Then you could have the lettuce being shipped, and then as the lettuce is shipped, there is another transaction that's added to the chain saying the lettuce has now been added into a specific carrier on a specific date and time, even if you wanted to down to the vehicle. If the lettuce itself has to be kept within certain temperatures so it doesn't go bad, then you could actually then have sensors inside of the vehicle that could measure temperature gauge. And again, this information can be constantly added to the blockchain, creating a very comprehensive record. And then eventually the lettuce is going to end up inside of a grocery store. From the consumer's point of view, then what they can do is when they go into the grocery store, you could actually then actually have the lettuce have a true record of entry about itself. And because of the way the blockchain secures the data, that data is verifiable and trusted. So you could actually then potentially have a QR code on the lettuce that a consumer could scan, and then they'd be able to see the history of where the lettuce came from, which field, all the way through down to when it arrived in the store. What's interesting though is that if, say for instance, there is an E. coli breakout again for romaine lettuce, then you can actually then use the entries within blockchain to actually help you find where the E. coli breakout started, and so you actually solve the problem at its source. So you jump on to the next slide, please. Blockchain is really part of Web 3.0, and you're going to see more information about Web 3.0, but essentially consider it as a way of thinking about how data is central to everything we're doing. Web 1.0 was just the basic internet. Web 2.0 was transactional. Web 3.0 is really about data and making that data available across all platforms in any environment. If you can go on to the next slide, please. And if we look at blockchain itself, it really is about taking us from where we've been in the past, which is an area where there was a lack of data and visibility, through to having a secure shared environment of data, the distributed ledger, that you can verify the entries and have that be a baseline that can be shared across an entire network. And the way that we work as companies and as consumers is that our networks are just becoming more complex. So if you have the ability to have a network that you can share easily and securely, then you want to take advantage of that rather than restricting yourself to a closed wall environment where you're having to constantly come up with ways to invite people into the content that they need. Next screen, please. So quick history of blockchain, and one of the things that you'll see is that blockchain has evolved incredibly rapidly over the last 10 years. The concept of behind blockchain as a way of sharing currency, or sorry, way of sharing money, came up with a white paper that was written by Satoshi Nakamoto on Bitcoin in 2008. Interesting factoid around Satoshi Nakamoto is nobody really knows who or who they may be. It's an anonymous party, but that party actually did a whole ton of work, and in 2009, the first blockchain technology, which is Bitcoin, was released, and the first product that was finally purchased with Bitcoin was a pizza, and that was purchased for 10,000 Bitcoins, and even at today's lower price of $6,000 per coin, that's still a very expensive pizza. I'm sure we're talking about tens of millions. What's interesting is with that very first set of tools for blockchain is that it really kind of helped form the foundation of having a distributed ledger that was very secure and kept complete records of every entry. What it didn't have was the ability to write comprehensive and complex programs and systems that ran on that distributed ledger. It had some very simple programming, but it was really, really simple. I mean, it didn't even include features such as looping, and the whole point of that was because it was just around currency, and the inventors really wanted to limit the functionality around that. What's interesting, though, is that none of this was really new. This was all built on technologies that had been around for a while. The way that the transactions are managed and merged is not new. It's just a new way of applying those technologies. In 2014, another white paper came out detailing a new blockchain protocol called Ethereum, and this has really become the most popular developers platform for building out solutions. And with Ethereum, you have a tool that allows you to write truly comprehensive applications that can run on the Ethereum protocol. So you can actually have applications that run globally on the different nodes around the world. And there's over 6,000 Ethereum nodes today. In fact, that number may even be higher. And what you can actually do is write applications which are known as smart contracts, written with a programming language called Solidity, that can then actually complete and execute transactions. And you can think of smart contracts as similar to a real world contract. So a simple smart contract would be something like I'm going to buy some digital currency at this value and do that exchange. But a more complex smart contract could be the buying of a property. So I want to move ownership of a house from being with Mrs. Smith to Mr. Jones, and you can actually do the transaction using smart contracts and have that data being captured. There are still some restrictions with the blockchain 2.0 smart contract and distributed app world, and that really comes down to performance. And this is something that Todd and I have actually had some conversations on, and performance really is key. And when you're looking at having an enterprise solution where you want to be able to do tens of thousands of transactions per second, then blockchain is not going to be able to help you at the moment. With that said, it's 2018 and everything's moving at a really fast pace, and we're moving into really kind of a blockchain 3.0 world, and that 3.0 world is really addressing those weaknesses in blockchain, plus complementing and improving on the strengths, so the security, the distributed nature of the data, the ability to create world computing solutions with smart contracts. And EOS is a protocol that I'm really following very closely at the moment, that is that next evolution. And with that said, Ethereum isn't resting on its laurels, and they're doing some really interesting things there too. If you go into the next screen, please. So this is just really kind of the mechanics of how a blockchain works. We're going to skip past this right now because I know we only have a few minutes. So again, with a smart contract, it works as a similar concept to a real world contract. The way that the most popular language for it right now is Solidity. I would encourage you to read the Ethereum white paper, because they go into in depth on how to write smart contracts. There's also just a ton of great content on YouTube on how to develop and write your own smart contracts. Also dig through GitHub, because there's just a lot of great tools that are emerging. Truffle is one of them that I like a lot, which really kind of speeds up the development of smart contracts. The challenge you have with writing distributed apps and smart contracts today is that it really is console driven. I mean, you're getting down to brass tacks in your development code, and there aren't the tools that we are used to, such as IDEs, for building out these contracts today. It's really writing in raw code and executing everything in the terminal. That is changing very quickly, but that's where we're at today. So we go on to the next screen, please. So again, there are a whole range of contracts, and I think you're going to see the same evolution that's going to happen with smart contracts that have happened with the web over the last 20 years. The very first websites that came out were really, really basic websites that just replicated, handout flyers. Today we have extremely complicated websites, and if you're using Google Docs or any of the tools that are available online, you'll know that those tools have become very sophisticated, but they take time, they take a lot of work. And I think right now what we're seeing is just kind of this natural evolution from simple contracts, which can be written in a few days, through to complex ones, which will be developed with additional third-party tools in the future. So we can jump onto the next slide, please. So again, the concept behind blockchain is it's another tool for you to use. And what's great is that we have an increasing number of tools that we have to address business problems, and it's about building a better mousetrap. And I think fundamentally, particularly for new projects or projects where you have challenging problems, the concept behind blockchain and the ability to be able to share a distributed ledger is really going to be what powers the success of that technology in the future. And you can consider blockchain really being a foundation technology, along with how you manage and store your data, and how you would move forward. Something to point out is that there is really kind of divide in the two different types of blockchain you can have. There are public and private blockchains. Private blockchains being an environment where it's invite in, and there's a very active and a passionate group talking about the value of both. I think ultimately what we should be looking at is the value of growing strong blockchain environments, and I think whether or not they're public or private will really resolve itself in the future. What's interesting with blockchain as well is that it really becomes very complementary with machine learning and artificial intelligence. Certainly the volume of data you're going to have coming in on your blockchain environment is going to increase exponentially, and to help support the contracts that you have, you want to leverage machine learning to identify anomalies that come in. So for instance, with romaine lettuce, using it as another example, you should be able to, if you had a sensor on a truck and an entry was entered into blockchain saying that the temperature had risen above a specific threshold, you can use machine learning patterns to be able to trigger events. So we can go on to the next slide, please. We're just going to skip over the next couple of slides. It's really about building out your POC team. So we'll just go over the next one, and the next one, and the next one, and all these slides are available. And the next slide. So just to summarize, there are really three types of blockchain networks that we have available today. The first is really about, with blockchain one, it's really about just creating cryptocurrencies, and that's with Bitcoin. And there's lots of examples where the Bitcoin core technology, which is all open source, has been forked multiple times to create other additional coins. You have blockchain 2.0, which Ethereum, Hyperledger, Fabric. If you are interested in private blockchain networks, Hyperledger Fabric is one that you want to be looking into for building out these more complex smart contract driven solutions with distributed apps running across your peer-to-peer network. That's where we are today with blockchain 2.0. Blockchain 3.0 is really coming upon us right now. In fact, I was just reading that even at the moment with Ethereum, which is a 2.0 blockchain network, is being, there are things that are happening to the infrastructure that there are forks that will happen that will enable it to perform at the kind of performance that we expect through a traditional database. So we move on to the next slide, please. And this is just a really kind of overview of the frameworks. If we actually go on to the next slide, we have a visual that breaks down those frameworks. There's a lot of activity happening. I feel like this is an infographic that needs to be updated almost on a daily basis, but a couple of things that you want to look into is almost every blockchain solution I look at, whether it's the protocol, whether it's the tools, whether it's frameworks, is open source, and that has become really a baseline entry point for all solutions that are in this market, which is great. What's interesting is that then that you have a huge amount of innovation that's happening. There are 3 companies that, 3 of the big technology companies that are innovating heavily, Microsoft, IBM, and Accenture. Accenture is looking at creating really a small army of blockchain experts that can build distributed apps that can work with businesses. IBM has focused on developing the protocols and with them integrating those protocols into their Watson platform. The Hyperledger Fabric is a solution that was developed between IBM and the Linux Foundation. It is open source and it's really designed for the private blockchain networks that you want to create. It's very interesting. The positioning that Microsoft is taking for building out solutions on their Azure platform is that they are going to be neutral to the different protocols out there. They actually are not going to come out with their own protocol. They're actually going to be neutral. And the current tools they have run on top of Ethereum, but they have plans to adopt other protocols such as Hyperledger Fabric in the near future. You may want to check out, they have a really cool tool called Azure Azure Blockchain Workbench, which is a collection of tools that can really speed up your ability to build and release distributed apps onto an Ethereum network. Really, really cool stuff. So on to the next slide, please. This is just really talking about artificial intelligence and integration with blockchain. And I think we can just go on to the next slide and kind of finish this up. So think of blockchain as where we are right now today. It's very much the early days of innovation. I kind of liken it to it being like 1993 was for the web. And there's just tons of potential, lots of excitement, but there's also a lot of unknowns. A lot of time people just really don't understand what the value of building out a solution on blockchain is. That's going to materialize with more and more solutions that are built with blockchain over the next few years. The difference between the web in 1993 and where we are today with blockchain is that in 1993 with the web, you had to train people on what digital was. They didn't know that. You had a very small group of people that were computer savvy enough to be able to connect to the internet. Connection speeds were very slow and very expensive. And it was just a very complex experience. If we move forward to today, we have billions of people that are connected to the internet on a daily basis. They're digitally very, very savvy. And blockchain itself is a foundation technology that is digital in nature. So it's really just a matter of when that great blockchain solution gets built that isn't a Bitcoin-like solution, but one that actually helps your everyday life for blockchain to explode in popularity. And I think that will happen within the next year or two rather than when. So it's very exciting times right now. So with that said, I'm going to hand over to Zach.
Hello, hello, hello. My name is Zach Cole. I am CTO of Whiteblock, and I'm coming at you live from sunny Los Angeles, California. How's everyone doing today? Can't hear you, but I'm going to assume you're doing pretty well because you're listening to me. So I'm going to get started on my presentation, and I am talking about blockchain performance. Let me see how I get this going real quick. Sorry. Let me get the, there you go. So here are some of the challenges that we've encountered. I'm going to talk about the company and everything we've done later. So some of the main challenges in blockchain development these days is scalability presents a major bottleneck. Obviously, everyone knows that. Matthew touched on it. One of the primary problems is that public test nets are hard to build and they consume a lot of resources. And these test networks are needed to validate performance. There are no standardized or commercially available utilities, and the test nets depend on volunteer cooperation. So the results aren't reliable, they aren't deterministic, they're not repeatable, you don't have any control. Since this is an asynchronous process that operates within a decentralized or distributed environment, we need to really rely on the participation of these people to really understand the effects of these protocols and algorithms and applications once geographic distance has been introduced, because you know, a blockchain is only as fast as the slowest node. So a lot of time and resources go into launching the test net, but once it's launched, there's no guarantee that anyone will participate. Last year I was working on a project. They raised like $40 million. It took them 6 months to launch their test net. And once they launched it, there were only about 20 or 30 nodes that were participating in that test net. So when there are 20,000 like full nodes in the Ethereum network and millions of participants, how are you going to, how is a group of 30 really going to be indicative of real world performance? So it's not. It's going to be suboptimal. So what is the real bottleneck that's preventing the further adoption of blockchain technology and like our ability to scale? So let's talk about blockchain. This kind of touches on some stuff that Matthew already defined, but distributed ledger technology is it's also referred to. It's a single state ledger that's shared among multiple nodes. Each block refers to the previous block. These are like generally Merkle functions, so it operates similarly to a Merkle tree. It can be represented as like an immutable inverse single link list, because with a single link list, each block refers to or with a single link list, traditionally every unit refers to the next unit, but this is inverse because each unit.
Sorry, Zach,
yes.
Can I just interrupt you really quick? We're not seeing your slides advancing, so I'm not sure if you're frozen as well. No, so if it's okay, let me just give it back over to Todd, and he can advance it for you. Okay, yeah.
Okay. See the whole thing?
So we're seeing both monitors, it looks like.
All right.
Or I can have Todd do it for you. It's
okay. Is it still showing the notes? You're still seeing the?
Yeah, the next slide. Is it in? Yeah, you want to try it again? You want me to send it back to you? I'll send it.
Huh?
Now I've lost you. There we go. Looks good.
Okay, sorry about that, guys. Anyway, so in a traditional single link list, everything is referring to the unit that comes after, but whereas in blockchain refers to the one previously, so it can be considered that, but essentially it's a Merkle function. So it records transactions into chronological bundles based on validators or miners. So when a new entry is added to the ledger on one node, it's broadcast to the rest of the network via gossip protocol, and everyone establishes consensus to say, yes, this is valid, and then it's added to the block. So what's cool about blockchain is that it addresses the Byzantine generals problem. That was presented back in the 80s, and that's just like an essential problem in distributed computing systems. So like a number of players that are all separate from one another, they must agree on a particular state. But these players don't necessarily trust one another. So it's traditionally referred to as like the three generals problem or the two generals problem. It's these generals are outside of a fort, and they're all trying to coordinate when to attack, and they need to agree on whether or not they should attack, what time they need to attack, all of that stuff. But how can they communicate that to one another effectively? Because they're separated. So they can send a messenger, but that's not going to be reliable. They can, you know, send a smoke signal, and the wind can blow away the smoke. They need to all coordinate and understand this and agree on that particular state. So blockchain addresses that with, you know, game theory and consensus algorithms. So that's pretty interesting about that. And let's move on. So consensus algorithms, like asynchronous process that allows multiple independent parties to agree on the state of a particular data point. So that ensures Byzantine fault tolerance in the blockchain network and eliminates the need for trust. And there's a variety of implementations. There's proof of work that's traditionally found in Bitcoin. So that requires the node to provide mathematical proof of having expended a significant amount of computing power in order to participate in the voting process. And that's the process of validating those transactions and voting on whether a block is accurate or not. So they just generally have to like solve a pretty tough math problem to identify a nonce. And if the nonce value they put into that algorithm, if the output is equal to or less than the particular difficulty threshold, then that nonce is valid and they're allowed to submit the block. Proof of stake is trying to eliminate a lot of the overhead that comes with proof of work. So that just requires a node to actually possess a certain amount of tokens in their wallet in order to participate in the voting process. And DPoS is something that DPoS is something that EOS is presenting, and I don't know if this is Byzantine fault tolerant, just based off of what I've read and seen and tested with the EOS network. So I don't know if their DPoS is necessarily fault tolerant, but that's where the nodes they can vote themselves. They're voted into office either by the community or some other authority, whether it's algorithmic or not. And there's a lot of different flavors for each one of these. So for performance, I have this thing, it's called blockchain triad, right? So there's performance, decentralization, and security. In order to have more of one, you have to sacrifice the other. But these are the three elements that I generally associate with blockchain. Decentralization, you know, meaning political and architectural decentralization, and security, meaning that it's backed by cryptographic proofs. So let's get into a little bit about Ethereum. Yeah, it was like blockchain 2.0, you know, like Matthew was saying. So that was based on Bitcoin. It's a public blockchain, fault tolerant, Turing complete, implemented an application layer on top of the blockchain. So what Bitcoin did was cool. They created this foundation that everyone could build off of. And what Ethereum did was allowed users and developers to apply logic to transactions, like business logic, like this transaction will occur, the smart contract will release these funds when these environmental conditions are met. And that's pretty cool, because now using that, we can do a lot of other cool stuff. So the scripting language is Solidity, which kind of sucks, but it's what we're working with now. Some other systems implement other smart contract oriented languages like C++ or whatever, depending on which system you're working with. So I think that really launched some global awareness for blockchain, because it was more than just this platform for transactions specifically, like me sending a transaction to you. We can also apply business logic to these transactions, and we can make it do a bunch of other really cool stuff. So cryptocurrency itself is used to incentivize users to play by the rules. The thing is like it pays more to just play by the rules and ensure the security and the health of the network, rather than trying to be a bad guy, because you're going to be penalized. If you're operating in a proof of work system, the amount of computational overhead and hashing power that's required in order to do something bad, it costs a lot more than it would to just say, hey, I'm gonna keep in continuing to ensure the health of the network. So here's a quote from an early Bitcoin adopter, Maya Angelou: if it's true that a chain is only as strong as its weakest link, isn't it also true a blockchain is only as fast as its slowest node? And I think that rings true because it's an asynchronous process. So when we started out, we had a hypothesis. We're going to create a testing platform that's going to address a lot of those issues that we were talking about earlier. This is a full testing suite. Whiteblock is a framework for testing. We have a platform that allows us to spin up multiple nodes, allows us to apply IP addresses and VLANs to each one of those nodes, so they're operating within their own unique segment of the network that's actually logically separated from one another, and then we can apply latency, packet loss, all kinds of network impairments to these links, so that way we can actually observe how these nodes will perform in the real world. And we can also automate a lot of processes and transactions between these nodes to ensure that they're performing the way that they should be expected to. So some of our earlier test series were pretty basic. We were saying, hey, latency and miner profitability, what is the effect of network latency on a miner's ability to profit within the Ethereum network? So we built out a private Ethereum testnet. We applied 50 milliseconds incremental latency on nodes 1 through 6. So 50 milliseconds on 1, 300 on node 6, right? And 0 milliseconds of latency, so no latency on nodes 7 through 12. That was our control group. So the ability to control this latency allowed us to manipulate block propagation time and observe the effects of this block propagation time, this increased block propagation time, and this latency on the performance of these protocols. So equal computing resources were applied to each one of the nodes. So the only variable was latency. The nodes mined for 2-hour intervals, and then we checked the wallet balance after each test run. It was a pretty primitive test, but we ran it a lot and it seemed to be doing pretty well. So at the end of our test series, the results indicated that the control group had a 25% higher balance on average than the test group. So that means that that amount of latency had a significant effect on the ability of these these miners to actually profit. So what do we do with this information and what does it mean? One thing that it would mean is that it weakens security because latency increases the block propagation time. Higher block propagation time reduces transaction speed, increases the rate of uncle blocks, which are stale blocks, and it weakens the absolute security of the network against attacks. So if the stale block rate is around 1.97% and the bad actor, then the bad actor won't necessarily need 51% control of the network in order to launch a 51% attack, but it would actually require less. That was our initial hypothesis, and then I was at EdCon, which is the Ethereum Developers Conference in Toronto. I think it was in March or something like that, and the guys from Amber Data actually presented their hypothesis. That was if there's greater than one uncle per 2 blocks, the 51% attack only requires 38% control of the network. So the 51% attack is like the ability of a bad actor to control the blockchain by establishing control of the majority of the network hashing power. So that means that they can control which blocks are actually going to be added to the chain because they control a higher amount of hashing power within the network. So this can interfere with the process of recording new blocks and adding them to the chain, and can monopolize all of those processes and a lot of the performance, and prevent other miners from completing blocks. So then theoretically they could double spend and control the blockchain. So that's pretty dangerous for like a decentralized and distributed system, because that's where all the value comes from. So that also increases the likelihood of miner centralization. So if we assume that our network has 1,000 pools with 1% hash power and one pool with 40% hash power, 70% of the time we can assume that the latest block has been produced by a miner in the pool with a lesser hashing power. The rest of the network hears about the latest block creation in 12 seconds. So the other 30% of the time, The pool with the greater hashing power produces the latest block, and they instantly know that they must start mining another block. So since it's a gossip protocol, propagation of that news that a new block is being created within the network is slow, because I'm telling the guy next to me is telling the guy next to him. It's kind of like, you know, that game when you're a kid and you like whisper in someone's ear and then they pass it on. I think it's called like telephone or something like that. So we can assume logically that the last node in that network is going to hear about it, and the rest of the network has already started mining on a new block. So that last node is still going to be mining the last block. What do they do with that block? That block is considered a stale block, referred to as an uncle block in Ethereum. It's referred to as an orphan in Bitcoin. So that block isn't included in the canonical chain. It's essentially useless. So also using that understanding, like a percentage of the network hashing power is going to waste because it's being devoted to these uncle blocks or these stale blocks that aren't going to be used at all. So that weakens the absolute security and also the decentralization of the network. So we can see here a chart of the uncles per 50 blocks. So that's it comes and goes, and I think that this has a direct relationship with the block time, and we'll get into that. So test series A, our conclusion was low block times are more sensitive to latency. Latency has a dramatic effect on blockchain performance. High latency is a high block propagation time, which is a high uncle rate. The high uncle rate equals lower transaction throughput. So since these miners are processing, the miners that are processing uncle blocks are also hey. So the miners that are mining these uncle blocks are mining older transactions. So they're dedicating their resources and their hashing power to mining these older transactions when there are new transactions coming into the network. So that's going to lower the amount of transactional throughput. So what do we do about that? Do we increase the block times? Do we increase the gas limits? If we increase the gas limits per block, that's going to allow for larger blocks. So we're going to also have to inversely increase the block times as well, because the larger the block, the slower the propagation time. If the block time is somewhere around 12 to 17 seconds as targeted in Ethereum's difficulty algorithm, we need to take into consideration what the network propagation time is going to be. How long is it going to take for that last node to hear about the latest news? So we wanted to expand upon that in our second test series. We wanted to test a 51% attack and validate the results of our test series A. So we wanted to simulate a 51% attack. So our hypothesis was that a high uncle rate has certain implications on security. When the uncle rate is high, the amount of control over total network hashing rate actually requires less than 51% attack, 51%. So we wanted to validate that. Our hypothesis was it was less than 51%. That doesn't necessarily mean that we're trying to find 35% or anything. We just wanted to see if we could control the creation of blocks with less than 51% control over the network. So our methodology, we used our platform. We provisioned the network for 4 nodes, applied high degrees of latency to force a high uncle rate, and 3 nodes were configured as normal miners. 1 node was configured as the super node that controlled 46% of the network hashing power. The block time was 1 second, 1.06. There was a 57% uncle rate, 80 millisecond round trip latency, and we ran the test for 1,000 blocks. So our results showed, one on the right is saying this is what our block time was. The left is showing how much gas was used per block, and 20,000 or 20 million was the default gas limit using in Ethereum. So that means this is how much gas can be expended within this block. So our total block time was 1,046 seconds. Our total transactions were 30,000. Our transactions per second were on the high end, but that's because these were all running local to one another. Our uncle rate was 57%. So at the end of it, we could see that the super miner controlled 52% of the network, with 45% of the hashing power due to the centralization resulting from network latency. So that 45% is less than 51%. I think that validated our hypothesis right there. And this was just a very basic test. And so what do we do with these results? Where do we go from here? So our next test series was bigger blocks, bigger block time. So one solution would be raising the block time and the gas limits per block. Higher gas limits, bigger blocks, more transactions can fit in a block. There's going to be some trade-offs here, and there are going to be some implications. Luckily, we didn't really change the source code or have to do anything like that because we were working with one of our clients, Ubic Technologies, and they're a cryptocurrency that's similar to Ethereum. They actually are an Ethereum fork, so they just took guest source code and they wanted to address some essential shortcomings that they identified within the Ethereum network. So they implemented a custom difficulty algorithm referred to as Flux, which targets an 88-second block time. So rather than adjusting total difficulty after every block in the same way that Ethereum does, they reference an average of the previous 88 blocks. And they wanted to test and validate that they could raise their default gas limits from 4 million to 30 million. And they wanted to validate that those changes wouldn't negatively impact performance. And they also wanted to benchmark the performance of their difficulty algorithm against Ethereum's. So we set up test nets for both Ubic and Ethereum to run in parallel, 30 nodes in each network, 20 mining nodes, and 10 sending transactions. And each test series enforced different gas limits. So we did 4 million all the way up to 80 million. And the 4 metrics that we tried to pay attention to were transactions, difficulty, block time, and gas consumption. So the results indicated that throughput was higher for Ubic under the same conditions. Their difficulty algorithm implied a higher stability, more consistent block times. The uncle rate was also much lower, so that was really important because I wanted to, because what our hypothesis was is that a higher gas limit would have a bigger block, a higher block time would allow for the propagation of those bigger blocks, and that would lower the uncle rate. That would increase transactional throughput. So there's a correlation between uncle rate and throughput. And that was our last test series. I didn't add the newest one. Right now we're working with Syscoin. Syscoin is an early fork of Bitcoin, and it's really complex. They implement a function of master nodes similar to Dash, and then they also implement their own zero confirmation protocol referred to, it's a ZDAG, so zero confirmation direct cyclic graph. So what they do is they create a topological sort that orders the transactions based on dependencies, and then they run that topological sort through a Hawick circuit detection algorithm, and that can identify potential double spends. And if a transaction is identified as a double spend or a potential double spend, it's flagged, and then it reverts and defaults to proof of work in order to validate those transactions and ensure that a double spend didn't actually occur. But otherwise, if there is no flag, generally we can assume probabilistically that that transaction is valid, and we can spend our tokens immediately as soon as we receive them. So that allows for pretty quick transaction times, not necessarily transaction times, but it allows for a degree of assurance that these transactions aren't double spent and that they're actually valid. So it's really interesting. We're not done with that test yet, and I'll probably be presenting that at my next talk I give. But so let's talk a little bit about the white block platform. So scalable number of nodes. I think that we're moving into the cloud, so theoretically we can have millions. Right now we're just running everything locally, and we have about 6 servers right now that are set up. And as we're developing our product offerings, so we're using our own testing like tooling and utilities for our testing as a service, and we're also developing and productizing those tools and utilities to allow users to perform tests on their own using using the white block platform. So you can run a test, you can set up an environment, and it's very quick and saves a lot of time, and it also saves a lot of money because now you don't need to hire a $300,000 blockchain engineer. You can actually just hire a junior dev, anybody that can use a GUI can run these tests, and it's very much more affordable. So we can increase the number of nodes based on the user requirements. Transaction automation, we can do millions of transactions per second if we need to. We automate reporting, data collection, and visualization. We also have an IDE implemented that allows you to deploy smart contracts and compile them to the white block network. And so this is and then also we display metrics like transactions per second, like other network characteristics, what block number you're on. We have an explorer, so you can actually granularly check each block and see which transactions have gone through. And the whole thing is modular, so there's like a bunch of libraries that you can use depending on the system that you're testing, and it's actually blockchain agnostic, so we're not tied to any one particular client. So what are we doing? We're testing everything. We're working with the EEA, and we're working with the testing open work group. We're working with Hyperledger Caliper project, benchmarking utility. We're working with the Ethereum Foundation, and we're running some tests for Casper and sharding. We're working with Consensus. We're about to start working with them, and yeah. So if you want to learn more, you can check out the join the testing working group at the EEA. Join the EEA. It's cool. Check out the White Block website, learn about the basics of blockchain, join the community, and do whatever you want. Just learn and contribute and have fun doing it. Don't be a jerk to other people. So if you have questions or comments, feel free to contact me. Get me on Twitter, Telegram, LinkedIn, whatever. And I think that's it for me right now. So I will let Todd take over.
Thank you, Zach. Again, I want to thank all the speakers today, especially Matthew and Zach. Had the opportunity to get to know these gentlemen over, I guess it's several years now with both of you guys. So I think, with the three of us wanting to cover off on, this specific topic for this Vivid SIG Talk, you get three futurists, two topics in an hour. We went over a little bit, but I think all of this content is very relevant and timely for what's going on in the world today. But the future of APM, telemetry, and blockchain today on the 14th of August, you got it live. The replays are going to be available. Zach, if you want to hit the next slide for me, you'll see that there is a short survey. You'll be getting also an email with the survey, as well as links to the recording, and the presentation will also be available in a PDF download format. So all the links that we provided, all of this content, all of that will be made available to you as a registrant for this session. And then one last slide here is my formal thank you, not only to the presenters, but also for all of you as participants. I can still see that we have a number of people still participating. So again, thank you all for your participation in this event today, and look forward to seeing you on future Vivid SIG Talks. On behalf of the Vivid board, it's myself, Todd DeCapua. Thank you again, and we'll speak with you soon.